Hello. So we're going to cover in this video questions that are related to stuff that you did in sub-project number 1, where you were talking about all things buffers. So we covered titration curves on the last exam, so we're not going to have anything with titration curves on this exam, but we will have things about how to make buffers. Okay, and I don't have on the reference sheet, I do not have any equations related to making buffers, because the relationships that you use for making buffers are can be determined via just using dimensional analysis, canceling your units. So we're going to go through these examples and see how that works. Okay, so first we're going to be talking about just how do you pick a buffer, right? So we have the enzyme lysozyme, so that's our system of interest, and its optimum pH is close to 5. So that is our target pH. So we want to be able to pick a compound that is listed that would be a good buffer for working in this working with this protein. So our target pH is 5.0. Okay. So what's our rule for selecting a buffer? So for buffer selection, you choose a buffer with a pKa value within 1 unit plus or minus of your target pH for your solution. So we're going to be looking at the pKa values. Okay, so let's look at the table, and we're going to look at these pKa values. So let's just circle anything that would work at pH 5. So 4.75, that's within a unit of 5. 9.25, nope. 6.37 is it's a little more than 1, so I'm going to say no. 10.2, nope. 3.09, nope. 4.75, that would be good. 5.41, that would be good. Formic acid has a pK of 3.75, nope. And all these other ones are farther than 1 unit away from 5. So we have 2 buffers, citric acid and sodium acetate, that could work. So either sodium acetate or citric acid would work, because have pKa's close to 5. So, you have choices. Sometimes a compound will interfere with your assay for other reasons, but we don't have any of that information. But we do have information here that that would lead me to choose one of these compounds over the other. Okay, and I would say citric acid might be a better choice, because it has 2 functional groups with pKa's in this range, and thus it would have a higher buffering capacity at the same concentration. It just means, if you have the same number of molecules of each of those buffers, the citric acid has 2 groups that could lose protons, and so it has twice the buffering capacity. Higher buffering capacity at the same concentration. Okay. All right, so we want to make, in the next part, what we want to do is we want to make 1 liter, 1 liter of a 75 millimolar buffer solution. Okay, so I'm going to pick citric acid. Okay, and first I'm going to need to know how much to weigh out. So how much citric acid to weigh out. Okay, so I would need 1 liter times 75 millimolar, so I'm going to say 0.075 moles per liter. So that is 75 millimolar. I'll just put that there. And you need to have it in molar units because otherwise the units won't cancel. And then the other thing is we need to turn that into grams, and so we're going to use the formula weight of citric acid, which is 192.12 grams per mole. And so what does that wind up being? Let me get my calculator. And so I have 1 times 0.075 times 192.12, and that gives me 14.409 grams. So I would weigh 14.409 grams of citric acid. I would dissolve in, we're going to do a liter, so I'm going to say I'm going to dissolve it in 800 milliliters of distilled water. I'm going to adjust the pH to 5 with, hydrochloric acid or sodium hydroxide, whatever I need. Then I'm going to QS to 1 liter with distilled water. And that's how I would make my buffer. Okay. So that's how to make a buffer from a solid. Okay, we also make buffers by diluting things. Okay, so here we are. We have a stock solution of sodium acetate pH 5. So if we had that in the lab, we could just dilute it. So we need 100 mils of a 0.15 molar solution. So how would we make it? So this is where we do C1V1 equals C2V2. Okay. And in this case, we need to know what volume to use. So we're looking for V2 is our unknown. Okay, so our V2 is going to be equal to C1V1 divided by C2. Okay. Okay, so our concentration is the concentration of the original stock, so that's 1 molar. And then our concentration 2 is what we want it to be, which is 0.15 molar, or that winds up being 150 millimolar. And our final volume that we want is going to be, our final volume that we want is going to be 100 milliliters. And I incorrectly said what our unknown was. So our unknown is how much of the stock solution we're going to use. So let's do this. We'll do our V1 is going to be equal to C2V2 over C1. There we go. That's fixed. Okay, so let's plug in our numbers. We've got 1 molar for oops, let's get this right. We have C2. C2 is 0.15 molar. V2, 100 milliliters. And then C1 is our 1 molar stock. Okay? So we don't even need a calculator to do this. The math here, we're dividing by 1. The molar concentrations cancel out. We're multiplying by 100, so we're just going to move the decimal point 2 over. So that comes out to be 15. The units are going to be milliliters because the molars cancel. I'm going to do those in a different color so it doesn't. Let's do that in yellow so those cancel. Okay. And so now how are we going to make the buffer? We're going to take 15 milliliters of our 1 molar sodium acetate, pH 5. We're going to add distilled water to get to our final volume, which is 100 milliliters minus 15 milliliters, which winds up being 85 milliliters of distilled water. And stir to combine, and that is how you would make a buffer by dilution. It's a whole lot easier than making a buffer from a dry compound, and that's why we like to have stock solutions in our laboratory. And so that's it. That's the end of our videos.